Special relativity tells us time is just another dimension of space, but time seems to have some rather unusual properties. For example, I can travel back and forth through space, and space doesn't seem to be perpetually moving forward. So why does time seem so different? The answers are not yet known for sure, so today I'm just going to propose some candidate explanations. And just to be clear, I'm not a physicist, so definitely don't take my ideas too seriously. I'm just having some fun. I claim the reason time seems to always be moving forward is because of how our memories work. Hypothetically, imagine if the past, present, and future all existed simultaneously. But suppose the you that existed in each of those moments of time could only remember the past. As you examined your memories, you would see that they always seemed to be growing. You would remember that the you from 10 minutes ago could only remember the things that occurred before 10 minutes ago. And the you from 5 minutes ago could only remember the things up until 5 minutes ago. It would seem to you that time was always moving forward, even though each of those different versions of you were equally real. Well, brace for an extraordinary claim, because there are serious reasons to suppose that this may be the way reality actually is. Of course, this opens up many more questions. For example, why do our memories work only in one direction? This is because our brains, as well as all macro-scale entities in this universe, exhibit a property called causality. This is where causes tend to precede their effects. Of course, that still doesn't explain much, because we can ask, why do causes precede their effects? Why is this such a consistent property of pretty much all macro-scale entities? This can be explained with the second law of thermodynamics, which observes that entropy tends to increase monotonically. But we can still ask, of course, why does entropy increase monotonically? Well, it can be shown with statistics that if everything is traveling through space-time in a mostly correlated direction, then it is statistically improbable for anything else to occur. And it turns out that pretty much all the matter in our visible universe is moving through space-time in a mostly correlated direction. Of course, then you can ask, why is that happening? And the answer to that traces back to the singularity that precedes the Big Bang. And that's as far as we can go. Now, if you followed all of that, then there's no reason for you to watch the rest of this video, because I'm just going to go over that all again, except this time more slowly and include details and reasons. Let's start with a quick review of special relativity. Special relativity depends on two fundamental assumptions. First, there are no privileged inertial frames. This was observed by Galileo in his principle of relativity. You know when you're driving a car and it feels like you're sitting still and those telephone poles are just zooming right past you? Well, that's not actually wrong. And you know that joke about how Chuck Norris doesn't do push-ups, he actually pushes the Earth down? Well, that's not wrong either. Second, energy is conserved. This wasn't formally discovered until the 1840s, but the intuition for it is almost baked into Newton's laws of motion. Basically, you cannot get motion, or change of any kind, for free. The universe seems to take careful accounting, such that every action is paid for. So these two assumptions are pretty intuitive, but when you try to put them together, something very counterintuitive happens. You see, a moving car has lots of energy. That's easy to prove. So if you change your frame of reference such that the car is actually stationary, then where did all the energy go? Minkowski proposed a surprising solution. He suggested that everything was moving through four-dimensional space-time at a constant speed. We call this speed c for celeritas. Sometimes it is called the speed of light because it happens to be the rate at which light moves through space. But if we include time as a fourth dimension, then we can say everything is moving at this same rate. As you sit there watching this video, you are actually moving at this speed in the direction you call time. According to special relativity, there is no such thing as speeding up or slowing down in space-time, but there is such a thing as changing directions. It's pretty easy to comprehend changing directions in space. For example, suppose you are driving a car at a constant speed in, say, a northbound direction. Then suppose the road veers slightly to the right. Your total speed has not changed, but some component of your speed will then be taking you eastward, and you will no longer be traveling northward at quite the same rate. Similarly, if you were to get up out of your chair right now and start moving in some spatial direction, a tiny portion of the speed you travel through time would be affected, such that your total speed through space-time would remain exactly c. and this provides an explanation for how the universe conserves energy. The Lorentz equation describes precisely how motion through space and time affect each other. It tells us that the contribution of our motion through space is mathematically imaginary. Consequently, instead of forming a sphere, the vectors of all possible directions we can travel through space-time actually form a hyperbola. Let's use the horizontal axis to represent space, the vertical axis to represent time, and we'll draw a vector of length c to represent your direction of travel through space-time. This is called a Minkowski space-time diagram. Now suppose Alice is standing at a train station. We'll represent her motion through space-time with a vertical arrow, suggesting all of her motion is in the direction of time. We might also draw a horizontal line here. This line represents the hyperplane within space-time that passes through all positions in space at a moment in time that Alice would call the present. Now suppose Bob rides past Alice on a fast-moving train. We'll represent his motion with an angled arrow, suggesting some component of his motion is going through space, meaning width, height, or depth. If we were to use Newtonian dynamics, Bob's motion through space would have no effect on his rate of motion through time. So he is moving through time in the same present moment he shares with Alice and the rest of the entire universe. This suggests a perspective called presentism. According to presentism, the past is gone, the future is not yet written, and the present moment is all that is real. Presentism is very intuitive, but there's a significant problem with this view. It suggests that energy is not conserved. Special relativity suggests a different paradigm. Because motion through space is mathematically imaginary, Bob's motion through time, from Alice's perspective, is even greater than her own. This phenomenon is called time dilation. Observe that from Bob's perspective, he's not actually moving through space at all. That means 100% of his motion is in the direction that he calls time. To put that another way, Alice's arrow of time and Bob's arrow of time point in slightly different directions. Thus, time is not actually some kind of universal direction that we all share in common. Time is simply the direction that makes an inertial frame stationary in space. And the remaining three orthogonal directions are what, from the perspective of that inertial frame, we call space. So if time is not exactly the same direction for Alice and Bob, that means space cannot be the same hyperplane for them either. Some of the things in Alice's present will be in a state that Bob would call the past, and some of the things in Bob's present will be in a state that Alice would call the past. These differences are not mere tricks of light. They are not byproducts of the lag in time that it takes for information to be delivered to Alice or Bob's eyes. If special relativity is right, then Alice and Bob actually occupy different slices of space-time. In other words, special relativity is not compatible with the notion that Alice and Bob occupy only a single moment in time. If they did, then travelers would blink out of existence and would never be able to find each other again. But it certainly is possible for Bob to return to that train station. When he does, the moments he and Alice call right now will have become disconnected. If, say, Bob kisses Alice, he will be kissing someone who, in the interim, has aged slightly more than he has. In order for this to occur, Alice must occupy her entire lifetime and not just the present moment. At one end of her life, she is a young child. At the other, she is an old lady. But the present is just an illusion. It is a story we tell ourselves. It is one with no physical counterpart in reality. This perspective on reality is called eternalism. Eternalism is a perspective that some people dislike because it disagrees with their intuition. But we do not recognize what is right by its ability to validate our individual perspectives. We recognize what is right by its ability to remain the best available explanation for many perspectives, even when alternative explanations are given serious consideration. So it is not really scientific consensus that leads us to accept all the strange implications of relativity. It is the way relativity more accurately predicts the behavior of fast-moving things. Newtonian dynamics has certainly been given an abundance of consideration, but it just does not describe observable phenomena as well as special relativity. I'll offer two examples. Global positioning satellites depend on having accurate clocks. When scientists build such satellites, They must compensate for the effects of time dilation to keep the clocks on these satellites consistent with those that remain relatively stationary on the Earth. The adjustments they make are based on the Lorentz equation that describe how motion affects time according to special relativity. As another example, muons are known to occur naturally when cosmic rays collide with the upper atmosphere. But they decay so rapidly that they would never even reach the surface under Newtonian dynamics. But because muons travel very quickly, less time actually passes in their frame of reference, and we actually do detect muons raining down on us. Significantly, muon detectors are inexpensive, so you can actually measure this phenomenon for yourself if you are interested. Now, if you are convinced that special relativity accurately describes our universe, and if you're willing to let go of presentism and embrace eternalism, then we're ready to start trying to explain why time seems to move, even though it really doesn't. The way we know our memories are involved in our perception of time is pretty simple. When we suppress our memories with anesthetics, our perception of time goes away with it. And since the aggregation of memories is sufficient to explain our perception of moving time, there's little reason to suppose that we actually need some special sense or other explanation for detecting the passage of time. The implications of this are fascinating. Even if the universe is a static pattern imprinted on a four-dimensional space-time, it would still seem to us as if we always lived in a three-dimensional moment we call the present. That present would seem to always be moving forward through time, and the reason it seems to move is because in each of these present moments, we remember only the past. So as we observe that our memories have been steadily growing, we're given the false impression that the present is moving forward through time. Now you might object, but the present just seems so real, and you're not wrong. The present is real. But so are all those other moments in time, where you also imagine that you live only in the present moment. There's nothing wrong with using our intuition to try to understand the universe, but when the evidence conflicts with our intuition, it's time for intuition to take the back seat. The universe is not constrained to operate in ways that confirm our expectations. Next, we need to explain why our memories can only remember in a single direction. The reason for this is actually pretty simple. Our brains are physical machines. All macro-scale systems in the physical world, including our brains, exhibit a property called causality. That means effects are always preceded by their causes. But contrary to popular belief, causality is not a fundamental property of space or time. Rather, it is a property that emerges at macroscopic scales because of statistics. Causality is such a familiar concept that you might be tempted to exclaim, "Of course that's how things work." But notice that's not actually how things work in these spatial dimensions. For example, consider the direction of width. If the force of gravity pulls on something to its left, then we expect it to pull on something the same distance away to the right with equal strength. There's no direction to causes and effects when they occur in width. The same is true for forces that operate over height and depth. Further, in all spatial directions, forces decay continuously by the inverse square of distance. But that's not how we're used to viewing things in time at all. We usually imagine time by supposing causes can only precede their effects. So in time, there is always a clear and established direction of flow. And we usually suppose there are no long-distance influences in time, so the only way to affect the future is through its immediate past. But why is time so fundamentally different from space? Actually, according to special relativity, it's not. At the level of fundamental particles, nearly all physical interactions are symmetric in both space and time. In other words, time really does behave just like space. The reason we don't see long-distance influences through time is because of the scale. Remember, just 1 second of time corresponds with nearly 300,000 kilometers, or a little over 186,000 miles. So forces that decay by the inverse square of distance seem to our relatively slow brains to have only immediate effects in time. And it turns out the directional flow of causality is not actually a property of time either. That property emerges at macroscopic scales because the kinds of things humans call effects usually involve some transfer of energy. When energy is involved, something asymmetric happens. In general, energy flows from potential to kinetic to heat. That is, it goes from usable to being used to used up. When energy flows in this direction, entropy increases, and for statistical reasons, that tends to be a one-way process. This is why, in physical systems, causes must precede their effects. But before we act like the matter has been fully explained, let's be careful about a few details. Sometimes physicists equate causality with time by referring to c as the speed of causality. This is actually using a rather different definition of causality. The rate at which things travel through space-time certainly limits causes and effects, but it is not the reason causes must precede their effects. Energy can transition from potential to kinetic to heat at a range of values. For example, living things generally try to use up their potential energy as slowly as they can. By contrast, explosives try to make that happen as quickly as possible. This contrasts with motion through time, which is the very definition of constant in physics. So it would be a mistake to equate the increase of entropy with time itself. They're not the same thing. Some theoreticians have suggested that entropy may be the reason time seems to humans to move forward. But humans are local creatures. We can only sense what is immediately around us. But entropy is not even required to increase locally. Refrigerators, for example, have the ability to reduce entropy inside the box. But refrigerators are not time machines. You could shove a human into a refrigerator, but he would not go backwards in time. He would not even perceive time to move backwards. He would just get cold. So entropy is not the reason things move through time, but it is the reason causes at macroscopic scales precede their effects. And that explains why pretty much everything around us, including our brains, are affected only by events that have passed. Next, let's discuss why entropy always increases under common conditions, and how that leads to causality. Suppose Bob decides to pee into a swimming pool. We typically assume the individual molecules of pee will move randomly. If it were truly random, then there would technically be some very tiny possibility that all of those pee molecules might just come together and jump back out of the water, leaving the water perfectly clean again. Yet at some level, we all know what is really going to happen. The pee is going to diffuse gradually throughout the water until it is all uniformly tainted. But why is this possibility so much more likely? The reason is because that's not just one possibility. There are an unfathomably large number of ways those molecules could move that would result in becoming approximately uniformly distributed through the water. This is what we call a high entropy state. By contrast, there are relatively very few ways those molecules could move that would result in them separating themselves from the water. That would be a very low entropy state. To be clear, there is nothing impossible about low entropy states. It's just improbable for entropy to decrease more than it increases in a reference frame that is moving in a direction correlated with the particles. You might have never heard that last qualification before, so let me explain. Suppose Alice had a vehicle that enabled her to travel through space-time in a direction opposite of Bob. You might ask, is that even possible? How do we know physics doesn't somehow prevent that from occurring? Well, we don't. But remember, the most fundamental assumption of special relativity is that there are no privileged inertial frames. If you're willing to throw out half of all possible inertial frames, then you're creating an entirely new and very different theory with very different assumptions. There's nothing wrong with doing that, but for now let's contemplate what special relativity suggests. If Alice were moving through space-time in the direction opposite that of Bob, then time would seem to her to be moving backwards. This really wouldn't be as extraordinary as it may sound. Our directions of time become disconnected whenever motion occurs. This is just a rather extreme case of that. And in this extreme case, Alice would witness something very bizarre. She would observe all of those molecules of pee gathering together, jumping right out of the pool and returning to Bob. It would be the very thing that the second law of thermodynamics says is far too improbable to ever occur. And what does this tell us? It tells us that the second law of thermodynamics depends on all of those particles moving through space-time in a positively correlated direction. We generally take it for granted that all matter is moving through space-time in a positively correlated direction. That's just the way things are in this visible universe, and I'm very glad things are that way. If even a very small meteor were to strike the Earth at the speed of light, there wouldn't be an Earth anymore. So it's a very good thing that most of the motion of the matter all around us is approximately in the direction that we call time. But why is this the case? What triggered all of that motion in approximately the same general direction? If it was all caused by the Big Bang, then wouldn't we expect matter to be hurled in all directions? Indeed we would, but consider what happens if we zoom in a little bit. Suppose we draw a tiny sphere around some random piece of the cosmos, and we call this the visible universe. We would find that within this tiny region of space-time, all the matter was moving in approximately the same direction. As matter pulled on neighboring particles, we might expect swirls and eddies of motion to form. These are what we call galaxies. But ultimately, the majority of the motion is still in approximately the same direction, and that's what we call time. And that's as far as my explanation goes. Again, I'm not a physicist and I don't claim to know that my theory is right, but thanks for entertaining my musings on the subject.